So get warmed up for these last couple of examples. Remember everything you ever knew about logarithms, which is the same as everything you ever knew about natural logarithms, and how to solve an equation that contains natural logarithms. Just like in the last problem, when we had an equation that said e to the y equals, and we were trying to isolate the y, we used a natural logarithm to undo that exponent, undo the e-ing to get the exponent down. So similarly, we're going to use exponentiation, is the real word for it, but you could call it e-ing both sides, to undo a natural logarithm. So if I wanted to solve this equation for y, and notice my y, he's trapped inside absolute value bars, and those absolute value bars are trapped inside a natural log. So I'm going to have to undo this from the outside. What undoes natural logging? It's called exponentiating. So I'm going to exponentiate both sides. I'm going to make e a base on either side. So e to the natural log, those undo each other and cancel each other out. I'm going to come up here. That's the absolute value of y minus 1. On that side is going to equal e to the x squared plus 5. How do I undo absolute value bars? Well, those are undone with a plus or minus sign. So if I want to take the bars off the left side, I'd be left with y minus 1 there. I'm going to have either the positive or negative e to the x squared plus 5. And then one more step, if I'm trying to isolate y is going to equal 1 plus or minus e to the x squared plus 5. Now this wouldn't be a great answer to a differential equation problem because I have given something that's not a function. That plus or minus sign that's left in my answer makes my answer not a function. But if I had an ordered pair on my y function, I'd be able to take care of that. So watch for this kind of idea, using natural logs to using exponentiation to undo natural logarithms in these next two examples. All right, so here I have a differential equation. dy dx is equal to 5 times y. This is half a notch easier than what you would typically see on the AP test free response. But you might see something like this on the multiple choice. And it's our first one that we're going to have to exponentiate to solve. So we're just going to warm us up. Remember, my first step, I have to separate the variables. I want everything with an x on the right. I want everything with a y on the left. So I'm going to multiply both sides by dx. And then I'm going to divide both sides by y. That's going to give me dy over y equals 5 dx. Now that my variables are separated, I'm going to integrate both sides. The antiderivative of dy over y is the natural log. That's the natural log of the absolute value of y. Over here, the antiderivative of 5 is 5x. Don't forget your plus c. So I separated my variables. I found I integrated both sides, and then I found an antiderivative on both sides, and I've remembered my plus c, my constant of integration. The next step I like to take, it's okay, I'll do it in the regular order. The order that I like here, I'm going to say that the natural log of, do I know the natural log of 2? Might not like that. This one, I think we're going to wait and find the c a touch later. So let's do this. I need to get my y out, but my y is stuck inside absolute value bars, which is stuck inside a natural log. So I'm going to exponentiate both sides. I'm going to make e the base, and the two sides I had are going to become the exponents on the e's. Let's move me over here, and I'm going to say that now the absolute value of y is equal to e to the 5x plus c. At this point, let's get y by itself first. Y, if I need to undo absolute value bars, I can do that as long as I use a plus or minus sign on the other side. Y is going to equal the positive or negative. So y is going to equal positive or negative e to the 5x plus c. At this point, you could simply use your ordered pair and find c, and you would get full credit. You still have to make a decision about whether to keep the plus sign or the minus sign, but given your ordered pair, I think you would have no trouble. But notice that at this point, most of the time you're going to find that I, and or the textbook, is going to use like another little technique to help understand this problem a little better, to understand what that plus c really means in this context. We called it an initial value, so it has something to do with what our function value is sort of at the beginning of time. Remember we did an example 2 examples ago where we had e to the x minus y, and we said, oh, that makes me think of when I divided powers that have the same base, I subtracted the exponents. Similarly here, notice that this could have come from y equals positive or negative. This could have been e to the 5x times e to the c. Because now if I saw that problem, I would say, oh, I have e to the 5x times e to the c. I'm going to keep the same base and add the exponents to get 5x plus c. But notice also that e is a constant and c is a constant, so e to the c is a constant, and multiplying by positive or negative 1, positive and negative 1 are both constants. So positive or negative e to the c is really just going to give you some other constant number. For lots of other reasons, we use the letter a typically to take the place of that constant. So this is the same as saying y equals a times e to the 5x. And at this point, we have enough information to figure out what a is. We knew our ordered pair was 0, 2. So I'm going to say that y, when y, here I'm going to come to the side like I did those other, figure out my constant. So I'm going to come to the side when 2 is y, this is going to be a e to the 5 times 0. Well, 5 times 0 is 0. E to the 0 is 1. So 2 must equal a times 1. 2 is, I'm going to write my final answer, y equals 2e to the 5x. Notice I could at this point replace x with 0 and I would get 2 for y. I could also, I could take the derivative of y with respect to x. Let's do this. So this is me just checking that my solution, my y function, is a solution of this equation. I'm going to be able to find dy dx and show that it equals 5 times my original y function. So I'm going to find dy dx. dy dx is going to equal, that's a dx. The 2 is a constant multiplier. The derivative of e to the 5x is e to the 5x times 5. And so that's dy dx equals 10 e to the 5x. Probably half a notch easier if I don't multiply those together. 2 times e to the 5x times 5. Just notice, I'm supposed to be able to compare this and say in my heart, oh yeah, those are exactly equal. Well, look, here's the 5, and here's y. So my dy dx does in fact equal 5y. I just proved that my solution is correct.